Hello and welcome to our lesson on scatter graphs, lines of best fit and interpreting correlation. Today, we will dive into some essential concepts that will enhance your ability to represent and analyze data effectively. In this lesson, we'll expand on our existing knowledge of visualizing data by learning how to use scatter graphs and lines of best fit. Our primary focus will be on understanding how to interpret correlation. We'll start by discussing scatter graphs and how they can be used to represent paired data. Next, we will explore how to draw a line of best fit through the data points on a scatter graph. Finally, we'll learn how to interpret the correlation shown by the scatter graph, distinguishing between different types of correlation. So far, we have built a strong foundation in data representation by covering data terminology, including understanding population, sample, discrete and continuous data, and primary and secondary data. We have looked into grouping and organizing data to make it easier to interpret, as well as visualizing data using various types of graphs such as frequency tables, time series graphs, pictograms, bar charts, histograms, and pie charts. With this solid background, we can now move on to scatter graphs and lines of best fit. This powerful technique is used to identify trends and relationships between two variables. For instance, if we wanted to analyze the relationship between hours studied and exam scores among students, using a scatter graph and a line of best fit would enable us to visually identify any positive or negative correlation. This can help us make predictions and informed decisions based on the data. Let's get started. All right, so let's dive into the main concepts for today's lesson. A scatter graph, also known as a scatter plot, is a type of graph that shows the relationship between two variables. Each point on the graph represents a pair of values. For example, if we are looking at the number of girls studying chemistry in a class and the percentage of A-star grades they achieve, each point would represent the data for one class. On the x-axis, we might plot the number of girls, while on the y-axis, we could plot the percentage of A-star grades. When we map out all the classes, we get a scatter graph. Now let's move on to lines of best fit. The line of best fit is a straight line drawn through the scatter points that best represents the trend in the data. It may not pass through all the points, but it aims to be as close to as many points as possible, showing the general direction of the data. In order to draw a line of best fit, follow these steps. Look at the overall pattern of the points. Then, draw a straight line that seems to pass through the center of this pattern. If the correlation is strong, this will be straightforward. If it's weak, it may be more difficult, but you can still make an estimation. Now let's try using the line of best fit for predictions. Once we have the line of best fit, we can use it to make predictions about our data. We can use interpolation if we're predicting a value within the range of our existing data. To do this, we draw a line from the value on the x-axis up to the line of best fit, then across to the y-axis, or vice versa. For example, if we know the number of girls in a class and want to predict the percentage of A-star grades, we use the line of best fit. Through interpolation, we predict that a class of 25 girls will achieve 76% A-stars. If we need to predict outside our existing data, we use extrapolation. We extend the line of best fit beyond our known values, keeping the same angle of trend. For example, to predict the A-star grades for a class with 35 girls when we only have data for classes up to 30, we extend the line and then use it to make our prediction. Through extrapolation, we predict that a class of 35 girls will achieve 94% A-stars. Now let's talk about different types of correlation. Positive correlation is when both variables increase together. For example, this means that as the number of women in a class increases, the total mark in an exam also increases. On a scatter graph, this looks like an upwards diagonal trend. Negative correlation is when one variable increases and the other decreases. For example, if as the number of boys in the class increases, the total mark in an exam decreases, we see a downward diagonal trend on the scatter graph. Finally, no correlation or neutral correlation is when there is no clear relationship between the two variables. For example, there is no correlation between a student's height and their test score. The points would be scattered randomly with no clear pattern. Now let's talk about the strength of correlation. If the points are very close to forming a straight line, the correlation is strong. If the points are somewhat close to forming a line, but with more scatter, the correlation is moderate. If the points are very spread out and only loosely form a line, the correlation is weak. Sometimes we have to ignore some data points as they are outliers. Outliers are data points that do not fit the general trend of the rest of the data. On a scatter graph, they stand out as points far away from the line of best fit. Identifying outliers is important because they can help us understand exceptions or errors in the data. One critical point to remember is that correlation does not imply causation. Just because two variables have a positive or negative correlation does not mean that one causes the other. One example is ice cream sales and sunburns. As we can see from the scatter graph on the right, as the number of ice cream sales increases, the number of sunburns also increases. So there is a positive correlation between these two variables. But does this mean that buying ice cream causes you to get sunburnt? No. In fact, there is another factor which is causing both of these things to increase. In this case, it may be hot weather. Hot weather causes sunburns to increase, and it also causes ice cream sales to increase. So ice cream sales do not lead to increased sunburns. Whilst this example of confusing correlation with causation is relatively easy to spot, others may be more subtle. So always remember that correlation does not equal causation. Let's look at some real examples and practice these new skills. Suppose we have data on the temperature in degrees Celsius and ice cream sales in a city. We plot the data on a scatter graph. Step 1. Plotting the data. Each point represents a temperature on the x-axis and the number of ice cream sales on the y-axis. Step 2. Drawing the line of best fit. We draw the line of best fit, ensuring it reflects the general trend of the data. As the temperature increases, the number of ice cream sales also increases. Step 3. Interpreting correlation. In this case, if the line slopes upwards, the correlation is positive, indicating that higher temperatures are associated with higher ice cream sales. This makes sense, since on hotter days more people tend to be outside and wanting ice creams, whilst on colder days this tends not to be the case. So where did scatter graphs come from? Scatter plots were in fact developed by Francis Galton, a cousin of Charles Darwin, the founding father of the theory of evolution. Genius must have run in the family. In the 19th century, Galton created scatter plots to study the relationship between different variables. His pioneering work on correlation and regression analysis became fundamental to the field of statistics, helping us understand how different factors are related. In today's lesson, we explored the use of scatter graphs and lines of best fit to represent and analyze paired data. We began by understanding the basics of scatter graphs, which display the relationship between two variables as points on a graph. We learned how to draw a line of best fit through the data points, which helps to represent the overall trend in the data. This line allows us to make predictions using interpolation within the data range and extrapolation beyond the data range. We then discussed different types of correlation, positive, negative, and no correlation, and how to identify them visually. The strength of correlation was also covered, ranging from strong to weak correlations based on the closeness of points to forming a straight line. Additionally, we touched on identifying outliers, which are data points that do not fit the general trend. A crucial takeaway from this lesson is the distinction between correlation and causation. A correlation between two variables does not necessarily mean that one causes the other. By mastering these concepts, you can now effectively use scatter graphs to identify trends, make predictions, and interpret correlations in data.